Well, hello and welcome to Doc Onco's Physics Tutorials. My name is Keith Onco, and today what we're going to be doing is taking a look at solving a problem having to do with electric fields. In fact, electric fields from multiple point charges at some point P. So we would like to know what the electric field is going to be at that point up in the upper right hand corner due to the three charges at the other corners of this rectangle. What we have is we have some dimensions. We know that it's 10 centimeters from this charge. I'm going to label this. We're going to call this one number 1, number 2, and number 3. So I know that from 1 to 3 it's 10 centimeters. I know from 2 to 3 it's 8 centimeters. And we can get the distance from 1 to 2 using the Pythagorean theorem. So using the Pythagorean theorem, I have 10 squared is going to equal 8 squared plus, I will call that b squared, and b is going to turn out to be 6 centimeters. All right, so we'll label that right away down there. So we know the different distances. We also know, since this is a rectangle, that the distance between 1 and 3 is 10 centimeters, so that the distance between 2 and the point is also going to be 10 centimeters. So we know what that distance is, and the distance between, again, 1 and the point is going to be 8 centimeters, and 3 and the point is going to be 6 centimeters, just because it's a rectangle. So we have those distances down. So what we're going to need to do, all right, is we're going to need to figure out what the electric field is at that point up in the upper right hand corner due to each of the three charges. And we're going to do that by analyzing each one of the charges individually and then adding up the components from those charges individually. All right. So we're going to have to figure out x components and y components from each one of the charges. Okay, so let's take this in order and see what we can get here. Over on the right hand side, what I'm going to do is I'm going to build a table because I like tables. And ultimately, we need to know what all the components are from the different charges. So I'm going to build a table, and each time I get one of the components from one of the charges, I'm going to put it in my table so that when I'm done, I can simply add them up. So let's see what I've got. Well, looking back at what the equation is for the value of an electric field, the magnitude of an electric field is E is equal to K times Q divided by R squared. Now K is just a constant, all right, and that constant is equal to 9 times 10 to the 9th, and I'm going to leave the units out for right now. And actually, it's not exactly 9 times 10 to the 9th. It's like 8.98 times 10 to the 9th. But we're going to round that up to 9 just to make the math a little bit easier. Q is the value of the charge. So in our cases, it's going to be either 1 microcoulomb, negative 0.6 microcoulombs, and positive 0.8 microcoulombs. All right, now, do we include the negative sign in the equation? The answer is no in this case, and the reason is that these are vectors. Electric fields are vectors, and so what we need to do is we need to look at the direction of the vector relative to the point that we're interested in, okay? And depending on where that point is, the direction of the vector can be different. Okay, so we're going to look at it relative to the point in the upper right-hand corner right up there. All right, so let's look at, we're going to label these E1, E2, and E3. And before I do any math or set up any equation, I'm going to look at the value, or I'm sorry, not the value, I'm going to look at the direction of the vector relative to that point. So let's look at the direction of the vector from electric charge 1, all right, to the point P. Well, from electric charge 1, we know that any positive charge, and we know it's positive because it's got a plus sign over there, all right, And so the direction of the vector is going to be away from the positive charge. So it's going to be away from the positive charge. It's going to be going north as far as this point here is concerned. So my vector direction is going to be in the positive y direction for that electric charge. Now let's look at E3. E3 is also positive. So it's going to be going like that as far as the electric charge is concerned. And so we're going to draw a little line over here, and that's going to be in the positive x direction. So far these are pretty easy because we don't have to break any of these up into components. They already are components. Right? The first one, E1, is a positive y. The E3 is positive x. So we're lucky so far, but we're not going to be quite as lucky with E2. E2 is negative 0.6 microcoulombs. So what's the direction of the vector going to be? Well, it's going to be pointing away from the point because negative charges always sink. The electric field always sinks at the charge, right? And so it's going to be going in that direction. So it's going to be at an angle like that. And we're going to have to break that guy up into its component parts, which we will do. But first, let's take a look. Let's actually calculate the values of the electric fields. The first one's going to be K, which is 9 times 10 to the 9th, times Q. Well, for E1, Q is 1 microcoulomb, or 1 times 10 to the minus 6th coulombs, divided by the distance between them squared. Well, that's 8 centimeters, or 0.08 squared. Okay. E2 is going to be 9 times 10 to the 9th times the value for E2, which is 0.6 times 10 to the negative 6th coulombs, all divided by the distance between them, and that distance is 10 centimeters, or 0.1 meters squared. And I'm leaving the units out just to save some room on the board here. E3 is going to be 9 times 10 to the 9th times 0.8 times 10 to the negative 6th coulombs divided by 0.06 meters squared. And the values that we get for these are going to be 1.4 times 10 to the 6th newtons per coulomb for E1. It's going to be 5.4 times 10 to the 5th newtons per coulomb for E2. And it's going to be 2 times 10 to the 6th newtons per coulomb for E3. So E1 and E3 I can add right away to my table. Well, E1 is in the positive y direction, so this is going to be 1.4 times 10 to the 6th. Okay. E3 I can add, and that's going to be positive in the x direction, so this is going to be 2 times 10 to the 6th. But now what I need to do is I need to break that guy up into its component vectors, okay, x and y vectors. Well, what do I have? I have a vector that looks like this, and I need to get the x and the y components, okay? I draw it like this to help me to know what the components are going to look like, because remember, this is the start of our vector, here's the end of our vector. And so my component also has to start here, right? And they need to end there. So my my y component has to start here and go down. My x component starts here and goes over to the left. So it's going to be a negative y component and a negative x component. So I can put the negative signs in there right now, all right, just so I don't forget them for later. How am I going to get this? Well, I can get it using trig, but I'm going to need to know the angle theta up here so that I can determine what the components are going to be. I already know the hypotenuse value. That's 5.4 times 10 to the 5th newtons per coulomb. I know that already. How am I going to get that angle? Well, The good thing is that I know the distances here. I've got distances. So if I were to complete this triangle here, all right, what do I have? I know that this is 8 centimeters over here. All right, I know that 6 centimeters on the bottom. So if I use the tangent function, all right, the inverse tangent, whoops, of opposite over adjacent, or 6 over 8, it's going to equal the angle right up there. All right, so I can get my angle doing that. And when I do that, I find that that angle comes to be 36.8 degrees. All right, so now I know that this angle up here is 36.8 degrees. All right, so I'm getting somewhere. Well, now I can use trig functions, sine and cosine, to figure out what the opposite side is, and the adjacent side. All right, so in this case, the y side is my adjacent side, and so I can say that the hypotenuse, 5.4 times 10 to the 5th newtons per coulomb, times the cosine of 36.8 degrees is going to get me this y value. Okay, so 5.4 times 10 to the 5th newtons per coulomb times the cosine of 36.8 degrees is going to give me that adjacent side, and that turns out to be negative 4.3 times 10 to the 5th. So negative 4.3 times 10 to the 5th newtons per coulomb. All right, and I'm going to add this in right over on my y table here. So negative 4.3 times 10 to the 5th newtons per coulomb. All right, so I've got my y value. In the same way, I can now figure out what my x value is, right? But this is the opposite side, so I'm going to need to use the sine. So it's going to be 5.4 times 10 to the 5th newtons per coulomb, 10 to the 5th newtons per coulomb, times the sine of 36.8 degrees, all right? And that value turns out to be negative 3.2 times 10 to the 5th, 10 to the 5th newtons per coulomb. So I'm going to go and add that to my table over here, negative 3.2 times 10 to the 5th newtons per coulomb. I have now accounted for all of my vectors, E1, E3, and then the components for E2. And what am I going to do? I'm going to add them up. So when I add up the y side, I get 9.7 times 10 to the 5th newtons per coulomb. And when I add up the x side, I get 1.68 times 10 to the 5th newtons per coulomb. Okay, I've got my x and my y components. And so we're almost there. We now just have to take those x and y components, rebuild a final triangle using those components, and come up with the magnitude of the final vector. So I'm going to give myself a little space down here. So I'm going to use this component here for x, this component here for y. They both happen to be positive. So my x component looks something like this, 1.68 times 10 to the 5th. My y component is a lot bigger, and I'm not drawing these to scale, but that's okay. Looks something like this, except it should be a straight line. So this is 1.68 times 10 to the 5th. This should be 9.7 times 10 to the 5th. And now I can figure out what my resultant vector would be by using the Pythagorean theorem. So 1.68 times 10 to the 5th, that should be a 5, squared, plus 9.7 times 10 to the 5th squared. And when I take the square root of that, what I come up with is 1.94 times 10 to the 5th newtons per coulomb. And that is my resultant vector. Right? And that is the electric field strength at this point P up here due to the three charges. So what did I do? I took each one of the charges individually and I calculated their magnitudes. All right. I then looked at the direction of these vectors. Two of them happened to be purely either in the x direction or the y direction. All right. And so I added them right away to my table over here on the right hand side. One of the vectors, E2, needed to be broken up into components. All right. Before I could break that into components, I had to figure out what the angle was, though. All right. So I got that angle, all right, using the dimensions of the rectangle. All right. I can get the angle here using the 8 centimeters, the 6 centimeters, and the fact that this is 10 centimeters. All right. I get that angle, use that angle now, all right, to figure out what the components are. But be careful that we only use the sides of the rectangle, the values of these sides, to figure out what the angle was. That's all we use those sides for. All right. Then once we have the angle, then we had to take this, right, the 5.4 times 10 to the 5th newtons per coulomb, and then break that up into its constituent components. Add them to the table over here, all right, here and here. All right, add up all of our components now, x components and y components, and then finally rebuild our triangle. All right. I hope that helps. If not, you can watch this over again. You can look at some of the other electric field tutorial problem solving sessions that I have, and hopefully that will help. Hope that helps, and have a great day.